Now we'll come to the acceleration component. Acceleration, the acceleration, we heard about the term. Acceleration is the rate of change of velocity. So rate of change of velocity. Acceleration is, better definition is the rate of change in velocity. Rate of change in velocity. Let you take at time t, some in a flow field, at time t, some flow having a velocity v. Some particular point, the point is, let you take x, y, z coordinate at time t, that is the velocity. And velocity is a function of the spatial coordinate as well as the temporal time. So this is a particular x, y, z coordinate, that is the velocity. Let you take here, it is the point. This flow. After delta t time, after time the delta t, the velocity becomes v plus delta v. Some changes is come in the velocity. And position also change. Position, how it is changed? X plus delta x, y plus delta y, z plus delta z. And time also you have seen change. That means some displacement is occurring at time t. At time delta t, some displacement occur, and particular location it is coming from here to here, some position, some location. So, and velocity also changes. So previously the velocity was a function of x, y, z, t. Now after t plus delta t time, the velocity is the new velocity. It becomes a new velocity. And it of the function, so it's a function of x plus delta x, y plus delta y, z plus delta z, and t plus delta. So according to the acceleration definition, the final velocity v plus delta v minus initial velocity by time. Time is the change delta t time. That is the acceleration definition you will get. So it is a, in this way we are getting it, delta v by delta t. That's the way. If the delta t time is very small, if delta t time is the very small time, tends to 0, so the limiting component will come here. This limiting component will come. Delta v by delta t. The limiting component will come. So in differential form, something it will comes in this dv dv dt. That is the way to getting it up. So velocity we are talking about. Now you think about the velocity also having a 3 component. Velocity having a 3 component. If a velocity, if you reserve the velocity in a Cartesian coordinate, so along x-axis it is y, along y-axis it is v, along z-axis it is w. So hence here, this v is a vector quantity. If it is a vector quantity we are talking about here. So one by one, if you are considering, so initially here along x-axis velocity was u, which is the function of the similar way x, y, z, t, and final velocity is the u plus delta u, which is the function of x delta x, y delta y, z delta z, plus t plus delta. That is the way. Similarly, the along x-axis, Cartesian coordinate we are taking along x-axis. The velocity changes from u to u plus del u. Along y-axis, v That is also some changes will come. Similar way. Same way. You write it down the same way. And is the along y-axis. And along z-axis, W, same way, W also changes. At t time, it was the W. Now, there is W changes is already same manner. Now we are going to analyze this one by one. Along x-axis, what is the acceleration? Along y-axis, what is the acceleration? So along x-axis, acceleration is ax. Along y-axis, acceleration is ay. Along z-axis, acceleration is az. So if you take this thing, so ax is the acceleration along x-axis. Ay is the acceleration along y-axis. And along z-axis, this one. So that is the total acceleration. So we have to go for first along ax, what is the value? Ay, what is the value? Az, what is the value? Then we'll getting the total velocity, what is the value in terms of the vector. So that is our analysis we are going to do right now. The total acceleration we are going to find it. Whether the acceleration is a velocity is a component of the velocity is a function of the spatial coordinate as well as the time. Now we rewrite this portion again along x-axis. So along x-axis, the velocity changes y plus delta u. Y plus delta u. So y plus delta u, we can write from the Taylor series expansion. If you go for the Taylor series expansion, y plus as u is the function of x, so del u del x into dx. As u is a function of y, as u is a function of z, as u is the function of t, that is the first order term we are writing. Similarly, higher order terms will come in terms of x square by 2 in this way. Higher order terms will come. Second order derivative into in this way it will come in the term of the square. So better to write it higher order terms. Higher order terms. So that is so what is the acceleration along x-axis? Ax. Ax can be written as the limit del u. Del u is the change in the velocity divided by the time, rate of change of velocity, where delta t tends to 0. So what is that? It's coming. So del u, so u will be cancelled out from both sides. So what is the del u? Del u is coming as a del u by del t we are doing. So del u, so if you divide it with this by delta t, so everywhere here also it will come delta t, here one delta t, here one also delta t will comes, and this will be gone. So you can rewrite this thing. Del u by delta t plus limit delta t tends to 0 dx dt into del u del x plus limit delta y delta t tends to 0. Keep this thing in mind, del u del y. Limit del z delta t, where delta t tends to 0, del u. That is the thing. So that is the curve because limit in the limiting. So what is that? The position change with respect to the time is nothing but the velocity, rate of change of displacement, but it is the velocity of the particle, where u was the velocity of the flow. U here is the velocity of flow. Eulerian description. This U we are getting from Eulerian description, which is a local time and space. Here, this is also UP, the particle velocity along the x-axis. That is the VP, particle velocity along y-axis, and this is the WP, particle velocity along the. These three terms is coming from Lagrangian description. But these are the terms, the double arrow we are making, these are coming from the Eulerian description. So rewrite this equation, it is getting like this way. Del U del T plus UP, particle of, so this is the particle velocity along x-axis. Particle velocity along y-axis. This is the particle velocity along z-axis. This is the AX. So this is the AX. Acceleration along x-axis. So this part is, you say, the temporal part, depends on the time only. This part is known as the temporal component. Is known as the temporal component. It depends on the time. Temporal component or local acceleration. Somewhere it is telling us the local acceleration. The temporal component. It is known as the advective component. It's known as the advective. In this way, we are getting the acceleration along this, the acceleration along x. Same way, if you finding out acceleration along y-axis, so here just change will come in the y, because instead of the u, if you here if you instead of u, if you change only v or w one by one, you will get this values. You try this thing, instead of the u, you change only v and rewrite the Taylor series expansion. Taylor series expansion. Here, why higher order terms are gone vanish? Because higher order terms are gone vanish, because if you see here, next term will come x square, next term all will comes, higher order terms will come next in this function, and in this function. Now our consideration is here, what will one assumption will made first? What assumption? This assumption is the neutrally buoyant particle. So neutrally buoyant particle means whatever the particle velocity, the same the flow velocity. That means the particle velocity, fluid particle velocity is the same as flow velocity. What does it mean? UP is equal to U, VP is equal to V, and WP is equal to W. So neutrally buoyant particle we are choosing, as well as one more analysis we can say, we are already tell delta T tends to 0. As the delta T tends to 0, the Lagrangian description and Eulerian description are merged, are the same, no changes. System itself a control point. As the delta T U changes, the same, delta T is very less, the system is itself a control point. So no changes. Or better to write it, control volume itself a system. So this is the two reason we can say that we can write it down this thing. The particle velocity is equal to flow velocity along x-axis, along y-axis, along z-axis. So that's why I'm rewriting this equation. It's a better understanding purpose. And one more thing I'm going to tell, the higher order terms will be neglected. Because if you divide it by this thing, at last, at delta t is equal to 0, so no change of the x coordinate, that is also tends to 0. No change of the y coordinate, that is also tends to 0. No change of the z coordinate. So higher order terms will all become 0. Higher order terms will all become 0 in this manner, because as the delta t tends to 0, so no, as there is a time is very short, so delta x also tends to 0, delta y tends to 0, delta z tends to 0. So it remains the same position, not that much change of the position is there. That is the consideration in this. So again, I'm rewriting this equation one by one. You're just trying to follow. So along x-axis, acceleration, that is the del u del t plus u. So particle velocity is equal to flow velocity. So that's why we can write it down in this way. If it is a not neutrally point particle or not delta t0, you have to write it up instead of the u in this case. Plus v del u del y plus w del u del z. Similarly, acceleration along y-axis, if you do the similar way, just only it is changed. It is a v dt plus send u dv dx plus v dv dy plus w dv dz. That is the acceleration along y-axis. And acceleration along z-axis plus u dw dx plus v dw dy. The same way it is repeating in this manner. That is the total acceleration. So total acceleration is another name, is the material derivative. The total derivative, it is known as the, actually we are writing this thing as a total derivative form. du, capital Du by d. Here, capital dv. Here it is capital dw dt. So d by dt is nothing but the total derivative. Total derivative. It is another name, is the material derivative. Somewhere it is still as the material derivative. Somewhere it is still as the substantial derivative. All are the same. All other cases is the same. So total derivative is the function of d by dt, local with a temporal component, plus u dx plus v d dy plus w d dz. This looks like this. That is the total. So first part is the temporal component, temporal derivative, partial derivative, it is a derivative, is the spatial derivative or adjective component. Is the spatial derivative. And with respect to x, with respect to y, with respect to z. Now in this case, if you write d by dt, you see that here we are writing in same. So d by dt. So total acceleration is axi plus ayj plus azk. That is the total acceleration. Total vector. In terms of the vector we are writing. Previously we are writing it the magnitude. Now we are writing in terms of the vector. So that is nothing but, what is this? Du by dt into I plus dv by dt into j plus dw by dt. So d by dt of ui plus vj plus wk. That is the total vector. D of total derivative of the velocity. So what is that? Total derivative of the velocity. So a is the total derivative of the velocity, dv dt. So d dt of partial differentiation plus partial differentiation plus in this term. What is this? In this part, how we can write it down? So in this part, if you take one separate page, here we are writing it down. Here you see, here I am writing u del x plus v del y plus w del z. That is the part. How we can write it in terms of the vector, in terms of the vector form. So introducing one part here, that is the known as the delta. Delta is nothing but I ddx, j ddy plus k dd. And v vector. So it is a vector. Say in terms of the sometimes in the scalar, if we taking with the delta operator in the scalar, we are known as the grad. With the vector, if we delta operator, if we take it's a divergent. So this way, v we know as the I into u plus j into v plus k into. If you perform v dot delta, if you perform this v dot delta, it will comes as the u ddx plus v ddy because it is a dot product plus w ddz. So this part is better to write in terms of the vector is the v dot delta. So this part we are writing it v dot delta. V dot delta is this part. That is into is the vector form of the total acceleration. What I am writing, that is the vector form of total acceleration. Again, I am telling it this thing. If you have any confusion, just the important part is d by dt material derivative is equal to del t local temporal part plus v dot v. That is it. So if you perform here dv dt, it will comes in this way. dv dt If you u vector, it will come simply u. If v vector, it will come simply. But this performance v dot del, v dot del. So v is of ui, vj, wk. That is the v. If your dot product with the delta is d dx, I of d dx plus j of d dy plus k of d dz. You perform this thing, it will definitely come u d dx, v d dy. This thing you should remember everyone. If any total derivative, you are going for the total derivative cases, any parameter now you change, it will comes in the same manner. Any parameter, I'm telling it, instead of the v, any parameter. If it is the rho, total derivative of the rho, density, so d rho by. So d rho by dt means del rho del t plus what does it mean? Del rho del t plus u d rho dx plus v d rho dy plus w d rho in this manner. So that is the way we are getting this acceleration, total acceleration. Total derivative is the part of the temporal component and convective part. That's all. Okay. So here we stop. Next we'll continue regarding the imaginary lines concept. Next one.